Yes.
Okay, perfect. All right, then, thank you very much. And I will jump right to it. We have already heard quite some introductions during this conference on EFTs and so on, so I will skip that. And I will give a slightly different approach here, where I'm looking at patterns in fundamental physics and try to understand how we can resolve them. So for example, we can have different realizations of the Lorentz symmetry. We have obviously the gauge symmetries of the standard model, and they can be implemented differently in BSM. There can be global symmetries, and especially among those we can have flavor symmetries, where here what I'm showing is just the flavor symmetry of the standard model in the gauge sector. Now, the very interesting question is, how is this realized in BSM? And we need different approaches in order to tackle the different symmetries or patterns here. We can address the Lorentz structure and the gauge structure in high energy observables, and I'll have one short example on that. And then most interestingly here, we will look at the flavor structure and see how this high-low connection that Gudrun has already pointed out, how this is really helping us to pin down the flavor structure of, or the possible flavor structure of BSM physics. So let's quickly look at how we can tell something about the gauge structure or resolve the gauge structure. I am here looking at two 4-fermion operators containing only left-handed quarks, 2 tops, and 2 light-handed quarks. One of them is an SU2 singlet state, and the other one is an SU2 triplet. And the way we're going to distinguish those in measurements is by introducing this ratio R, which is the ratio of up versus down PDFs. So if you look at the total cross-section of, for example, TT bar production, you see that this ratio R enters into that prediction. And therefore, if you are, for example, comparing your prediction to total TT bar production cross-sections, you will be sensitive to a specific value of R, namely here you will be close to the valence quark maximum, and therefore you will be probing the 3-1 direction in this parameter space. So if you plot that in 2 dimensions, we will be constraining this direction here, but your orthogonal direction will remain completely unconstrained. And this is exactly what you see. So the data set M that we fitted to here is really a data set that is close to this valence quark maximum. Now, in order to resolve this blind direction and to pin down the possible structure, gauge structure of those 4-fermion operators, you have to introduce more measurements. And here, the obvious way to go is to choose a different value of R. And we do that by probing it in a boosted regime, so a boosted TT bar sample. And you see that indeed you are sensitive to a different direction. You can do even better by introducing TT bar Z and TTW measurements that probe even more orthogonal directions. And by combining everything, you pin down a very narrow allowed region. And especially if your measurements were to deviate from the standard model predictions, that would give you a hint at the possible realization of the gauge structures in your UV theory, in this case, the SMEFT. Now let's look at flavor, and here we have already seen quite a lot in the last 2 talks. So in the, oops, I'm sorry, there is something missing here. In the top fit, we had a U2 to the 3rd power assumption, but not as nicely implemented as Felix pointed out, but it was really just separating the 3rd generation from the first 2 generations. So by doing that, you're left with 22 degrees of freedom, which is something that you can manage in a global fit. And obviously now, if you're interested in the flavor structure, this is way too simplistic, and you want to relax the assumptions on flavor. As Felix has already pointed out, in a completely flavor anarchic case, there are way too many degrees of freedom. There is no way we're going to be able to include all of them in a global fit and have enough measurements in order to pin down or to resolve everything fully. So we have to somehow choose a middle ground, and the way we go is MFV, minimal flavor violation, that Felix has also introduced very nicely. There are still too many for now operators or coefficients, but in principle, this is manageable in the near future. So what we do here is we look at the subset of the relevant operators in MFV, really as a proof of principle on what you can gain and what you can learn on the flavor structure by combining top and B measurements. So this I'm going to go very fast. This is really just in order to clarify our notation. We promote the Yukawa, so in minimal flavor violation, we promote the Yukawas to sporions, and then we do our sporion expansion. And what you typically get are objects like this that have a very specific transformation property under the flavor group. I just wanted to write that down in order to point out that here we have a flavor universal part or coefficient. A is really just a numerical coefficient. And then we have flavor breaking coefficients, B and C. And in principle, you have more, you can continue this series. But because of the very strong hierarchy in the Yukawa couplings, we can truncate that series very rapidly. And for actually most of the remainder of the talk, or actually everything of the remainder of the talk, I am going to neglect all effects that are suppressed by anything smaller than the top Yukawa. So you can do that, and then you can, for all of the operators, you can write down all the entries in the Wilson coefficient. So those are for the 2-quark operators. Those are going to be 3x3 matrices, and this is what Felix has already pointed out. So let's just jump over that. And here in Felix's approach, this was even scarier. This is the 4-quark operators, also just written down here in terms of the individual components. So how do we connect the top and the bottom observables? So obviously you could start with the full model and then match that onto the SMEFT. We don't do that. We just start at the SMEFT. We evolve it down to the weak scale. We match it onto the wet, the weak effective theory, which we then evolve down to the bottom scale, where we compute observables. And now the important part here is that this matching between the SMEFT and the wet, this is really flavor sensitive. So this is very sensitive depending on the flavor structure. And I just want to illustrate that with one example. If you're, for example, looking at BS to mu mu, so the BS to mu mu decay, you can introduce the O5Q1 operator that we've already encountered in Gudrun's talk as well. That could, for example, modify the TT bar Z vertex here. Now, this is just as a reminder, and minimal flavor violation, truncated as specified before. C5Q1 is a diagonal matrix with a flavor universal part A that appears on all the diagonal entries. And then we have a B that only appears in the 3-3 component. So if we want to do this matching, if we're interested in BS to mu mu, we want to match O5Q1 onto, so O5Q1 from the SMEFT onto O10 in the weak effective theory. And what you realize is that this can actually already happen at tree level. So there is a tree level matching here by simply integrating out the Z. And the interesting part is when you look a bit closer at the structure of this vertex there. Now, in minimal flavor evaluation, because C5Q1 is diagonal, it's only the diagonal component. So it's a sum over I of C5Q and then this combination of CKM matrices. Now, if you're looking at the flavor universal component here, you realize that by performing this sum, it actually cancels out exactly due to the unitarity of the CKM matrix. So the tree level matching is only sensitive to the B component, the flavor breaking component. So matching C5Q1 at tree level onto C10, you get only a contribution from B. And then at the one loop level, you get additional contributions. And this time it's mostly from the 3-3 component, and therefore you have sensitivity to both A and B. But if you look at that numerically, so you go and do the running and the matching and the running numerically, you find that the contribution of A phi Q1 to C10 is completely negligible as compared to the contribution of the flavor breaking B phi Q1. So basically what this tells you is that by measuring BS to mu mu, you will be able to constrain the flavor breaking part of C phi Q1, but the flavor universal part is going to be left almost completely unconstrained. So let's look at a little bit more complicated example by introducing a second operator, namely the triplet version of the same operator that I've been talking about by now. And we will also be needing, as Gudrun has already introduced, the minus and the plus combinations of those two operators. So there will be a contribution to BS to mu mu, as I've already pointed out on the previous slide. And here O phi Q1 and O phi Q3 both contribute equally, so it's only the plus combination that is going to be constrained here. And as I pointed out before, due to the tree level matching, we're only sensitive to the flavor breaking part. In B2XS gamma, there is no tree level contribution here, so everything is at one loop level, and here both A and B contribute with comparable magnitudes. So this will give us an additional handle on some orthogonal direction in parameter space. Okay, so far for the B observables. Now, if we look at the top observables, there is some interesting effects going on there as well. Here, I want to just look at one example of TTZ production, still only considering those two operators. So the dominant contribution here obviously comes from the gluon-induced TT bar production, where the Z is radiated off of a final state. And this will be sensitive to this capital A, which is just the 3-3 component. So A plus B, or A plus YT squared B. Now, if you include the quark-induced TT bar production, you can radiate off the Z either from a final state or from an initial state. And you will, by doing that, you will gain sensitivity to A and B with different coefficients. So you will constrain actually a different direction in parameter space. And if you do that, so here, what I'm showing is the result of a 4-parameter fit. We're fitting really A3, B3, A minus, and B minus. And I'm showing just the 2-dimensional projection of that. So the profiled constraints coming from this 4-dimensional likelihood. So you can do that, you get your constraint, but then you realize actually there is also electroweak corrections adding to this process. And this is something that is very often neglected in top physics because they're typically not as important as the QCD processes. However, here you can already see that there are many different possibilities to insert our SMEFT operators. And just by the multiplicity of the different possibilities here, we actually get quite a sizable contribution coming from the electroweak effects. And if you include them, you will see that you actually open up regions of parameter space that you previously believed to be unconstrained. So the takeaway message from here is that electroweak effects can, even in processes that already are QCD induced, they can be very important and have to be taken into account. So let's see how we can combine all of that into a global fit. Global, in this case, means our 4 parameters. So this is a fit only to top data. And the very interesting part here is it's again the profiled constraint. So it's a 4-dimensional fit. And I'm just showing the 2-dimensional projection of it. And you see that we can constrain everything, basically. We get a compact allowed region in the end. And this is really coming from the fact that top data by itself already has some sensitivity to the flavor structure. This is also a fact that is very often overlooked, but you don't need to combine B and top physics in order to have some sensitivity. You really have some sensitivity already coming from the top sector alone. Now, if you include BS to mu mu, something quite surprising happens, namely not much. And the reason for that will become very apparent on the next slide. But just as a hint, it's the fact that we are only sensitive to the B plus combination in BS to mu mu. So if we're looking at the projection on B3, there is always the direction in the B1, so the B1 direction where we can escape to. Basically, the B minus combination remains completely unconstrained by BS to mu mu. And this is why nothing much changes by introducing BS to mu mu in this projection here. Now, the second interesting thing or surprising thing happens when we introduce B2XS gamma, namely a lot. And this is surprising because B2XS gamma is a loop-induced process. So we expect to have not that big of a sensitivity. However, here we got really lucky because the combination of parameters that we're constraining here, it's more or less the 1 minus 2 direction, which if you look is exactly the direction that was previously left almost unconstrained by using only top and BS to mu mu data. So this really is a lucky coincidence that B2XS gamma is really constraining the orthogonal direction here. Now, if we look at still the same fit, but we look at a different projection here on the 2 flavor breaking coefficients, so B3 and B minus, you see the dramatic effect that including BS to mu mu has, the tree level effect. So we are constraining one direction extremely well, namely the B plus direction, and the other one is left unconstrained by this measurement. So it's still the only constraint is coming from the top data. And here again, if you introduce B2XS gamma, you will further narrow down this, this previously least constrained direction. And you can see that also if you zoom in to the interesting region there. All right, with that, let me conclude. We can now start to study the flavor structure in a global approach. And maybe the couple of very important takeaway points are that even the top observables alone can give us some information about the flavor structure. And electroid corrections matter in top observables, even if the process is also QCD induced. And finally, there is still a lot to do. We need many more observables in order to have a truly global fit. We need to be able to deal with fits of more than 50 parameters. We need more complete predictions, including the SMEFT coefficients or the SMEFT effects of B observables. And I'm very sure there will be more points coming up in the next steps of this endeavor. Thank you very much.
All right, thank you, Sebastian. Do we have any questions? Okay, well, I have a quick trivial question. XS is just anything containing strange quarks, or?
XS, yes. That's okay. the inclusive.
Okay, Gautier has a question.
Yeah, very quick one also. So you're constraining the BBZ direction with BS to mu mu. It's also constrained by Z to BB. Do you know which one is the most constraining constraint?
No, I don't know. So it is certainly true that there is many possible new observables that can be included, Z to BB, but then also delta F equal 2 flavor transitions and so on. And they will be, some of them will be very sensitive to those operators and coefficients. So that's why I'm saying there is still a lot to do. And for C to BB, I don't know if it's going to make a big change or not. It could also be that it's just sensitive to a different direction in parameter space. But it's definitely interesting and should definitely be looked at. Yes.
Thank you for the very nice talk.
Thanks.
All right, we got 2 more questions, but we're currently 8 minutes behind time. So I'm really sorry, Gudrun and Susanna, again. Could you post your questions to the Slack server instead? Thanks. Jack, if you're ready, could you share your screen?